welcome to the deep dive. Have you ever typed a few words into an AI and just watched it generate this detailed article or conjure up an amazing image or, summarize some super complex document in seconds? It really does feel a little bit like magic, doesn't it? But here's the core challenge we're diving into today. How do you actually take these massive, really powerful AI models from the research lab, where they're built and fine-tuned, and get them into a real-world product? Something you can actually use, like, every single day. It's definitely not as simple as just clicking some deploy button.
Oh, definitely not. It's a real engineering feat, actually. This whole process, it's about transforming these large-scale generative AI models from, fascinating experiments into systems that are scalable, super efficient, and just completely reliable for production. It's really where the, let's say, theoretical power of AI meets the hard realities of engineering.
Right. So our mission for this deep dive is to unpack that whole journey. We're going to follow a real-world example, building a text summarization microservice, from the initial fine-tuning all the way through optimization and, the final deployment. You'll get a kind of behind-the-scenes look at how these complex systems are actually brought to life. And our sources for today, they're a fantastic stack of technical guides, some research excerpts. They really lay out a clear, step-by-step blueprint for this whole complex process. It's kind of like having a backstage pass to the cutting edge of MLOps.
Exactly. And what's really interesting here is that the information we're about to cover, it'll give you a real shortcut to understanding the practices that are shaping modern AI development right now. We'll probably reveal some surprising facts along the way about just how ingenious some of the solutions are to get these models working for you.
Okay, let's pull back the curtain even further then. Before we even think about deploying anything, what is a generative AI model, like fundamentally, and how does it actually generate something like text?
Right. So at its foundation, modern generative AI, especially models like, say, T5, relies on something called the transformer architecture. You can sort of imagine it as a highly sophisticated two-part system. There's an encoder and a decoder. The encoder's job is basically to take your input, maybe a long news article, and process it, turning it into this rich, contextualized, mathematical representation.
So it's almost like the encoder gives the decoder a sort of highly compressed, very rich memo about the input, and then the decoder takes that memo and expands on it.
Precisely. That's a great way to put it. The decoder then steps in, uses that contextual memo to generate the output, your summary, for instance, one piece of information or token at a time. The T5 model is a canonical example of this text-to-text framework. Is very elegant. But the real innovation, the thing that truly made the transformer a game changer, is its self-attention mechanism.
Self-attention, okay.
Yeah. This mechanism lets the model dynamically weigh the importance of different words in a sequence relative to each other. It's how it captures really complex context and long-range dependencies much more effectively than anything that came before it.
That sounds incredibly powerful. So it's not just looking at words one by one, but it's constantly assessing how important each word is in relation to all the other words around it to get the full meaning.
Exactly right. Think of it maybe like a web search. When you type a query, the search engine compares it to millions of keys or labels, right?
Yeah.
And then it returns the most relevant values, the actual content. Self-attention works in a similar way, using query, key, and value vectors to intelligently figure out which parts of the input text it needs to focus on most intensely. It's how these models really start to understand nuance. And of course, before any of this can happen, the raw text has to be converted into numbers the model can actually understand. This starts with tokenization.
Right, breaking it down.
Yeah, breaking the text into smaller units. Often they're subwords, like empowers might become empower and acts. Models like T5 use specialized tokenizers, like sentence piece, which might have, say, 32,128 unique tokens. This allows them to process a huge range of text efficiently by recognizing these common subwords or phrases.
So this is how the raw text becomes a language the AI can actually think in, turning words into numbers.
Exactly. These tokens are then converted into high-dimensional numerical embeddings. These are essentially vectors, lists of numbers, that capture semantic meaning. Words with similar meanings will have similar embedding vectors, sort of like points close together on a map. And finally, because self-attention itself doesn't inherently know the order of words, we add positional encoding. This adds information about each token's position in the sequence. It's how the model knows dog bites man is very different from man bites dog.
Okay, understanding the inner workings, the attention, the embeddings, the tokenization, it's fascinating. But it also really highlights their sheer complexity and, well, size. So once we've built one of these marvels, what makes getting it out of the lab and into a real product so challenging? It sort of feels like the hard part, the training, should be over by then, right?
That's a very common thought, but it's really far from over. The main challenges in deploying these large-scale generative models come directly from that immense size and their huge computational needs, moving them from a research setting, which is often, a controlled environment with lots of resources, to a production environment that needs to be scalable, efficient, and super reliable. That's the biggest hurdle. Specifically, you run into issues optimizing for cost and memory during fine-tuning, making sure inference, the part where it actually makes predictions, is fast and portable, and then packaging the whole thing up so it runs consistently everywhere. It's a whole new ball game.
Yeah, I've always wondered about this. These models are so big. How do we even begin to fine-tune them without needing, I don't know, a personal supercomputer?
Right, and this is where tools like PyTorch Lightning become absolutely essential. You can think of it as the central nervous system for the training process. It's a lightweight wrapper around PyTorch, the underlying deep learning framework. What Lightning does is simplify and automate the entire training loop. It handles stuff like gradient accumulation, managing training across multiple GPUs or other hardware, even mixed precision training, all with fairly simple configuration flags.
So it clears away the engineering clutter.
Pretty much. It lets developers focus on the actual model logic, the science, rather than getting bogged down in all that boilerplate engineering code. It really cleans things up. And then for the data side, there's the Lightning data module. This is key for making data handling reproducible and efficient. It basically bundles up all the data operations, downloading data sets, pre-processing them like the tokenization we talked about, maybe adding task-specific prefixes like summarize, and then setting up the data loaders that feed data to the model during training, validation, and testing.
So the Lightning data module is kind of like the unsung hero here, making sure the model always gets its data perfectly prepared no matter how messy the WA stuff is, like a personal chef for your data pipeline.
That's a perfect analogy. And it's huge for MLOps, for managing machine learning in production, because it decouples the data logic from the model training code. This means better consistency, better reusability, and it lets, say, data science teams and ML engineering teams work on their parts separately. It really enables this sort of data as a service idea within an organization. So for our text summarization example, we'd use a specific text summarization data module for the 10 daily mail dataset. And yeah, it would append that summarize prefix for the T5 model, telling it what job to do.
Okay, that definitely streamlines the data side. But what about the model itself? We're still talking billions of parameters sometimes. How do you actually fine-tune that without needing just insane amounts of compute power?
That brings us to a really exciting area called parameter efficient fine-tuning, or PEF, and specifically a very popular technique called LoRA, which stands for low rank adaptation. The core challenge, as you said, is that fully fine-tuning a huge model, even a relatively small one like a T5 with 60 million parameters, is incredibly demanding on compute and memory. LoRA cleverly gets around this by introducing only a very small number of new trainable parameters.
Wait, hang on. So you're saying we can take a model with potentially billions of parameters and effectively teach it new things by only tweaking a few thousand? That sounds almost too good to be true. Are there trade-offs? Like, does it learn as well?
It sounds like magic, I know, but it's really ingenious engineering. Instead of retraining the whole massive base model, LoRA injects these small trainable adapter matrices into certain layers, typically the attention layers. Think of it like the original model weights are frozen, kept fixed. And you only train these small adapter matrices. The output is then a combination of the original output and the adjustment from these adapters. Mathematically, it approximates the change in weights using a low-rank decomposition, like WA, where B and A are much smaller matrices. The forward pass becomes something like HEWX plus BOX.
Okay, so you're adding small adjustments rather than rewriting the whole thing.
Exactly. And the parameter savings are genuinely massive. Take a typical layer, maybe 124 by 124. That's about 1 million parameters right there. With LoRA, using a small rank, you might only add, say, 892 trainable parameters for that whole layer. That's a reduction of over 99%. This is what makes fine-tuning these giants feasible on consumer-grade hardware, sometimes even a single GPU.
Wow, that is the genius of it then. It's not just a small optimization, it's fundamentally changing who can work with these models. It democratizes access. Someone with just one decent GPU can now fine-tune models that used to need a whole data center. That, for me, is the really surprising part, how clever engineering is making these massive tools accessible.
Absolutely. And when you configure LoRA, you set a few key parameters. R is the rank, which controls how many parameters you add. LoRA alpha is a scaling factor. Target modules tells it which parts of the model to adapt, usually the query queue and value V projections in the attention mechanism, and then things like LoRA dropout and bias settings for regularization and detail.
Okay, so LoRa sounds like it solves a huge piece of the puzzle. How does PyTorch Lightning then take this and, pull everything together for the actual training run?
Right, the PyTorch Lightning Trainer is the orchestrator here. It takes your Lightning module, that's where you've defined your model architecture, the LoRA adaptations, and the training logic like calculating the loss, and it takes your Lightning data module for the data. The trainer then automates the whole training process. It handles things like automatic checkpointing.
Saving the progress.
Exactly. And importantly, for PEFT models like LoRaO, the checkpoint only needs to save those small adapter weights, not the entire massive base model. So your checkpoints are tiny, maybe a few megabytes instead of gigabytes. The trainer also handles early stopping, so it stops training if the model isn't improving on validation data, preventing overfitting. And it integrates logging tools like TensorBoard Logger, so you can monitor how the training is going. For a production-ready setup, you typically set configurations like Accelerator Auto and Devices Auto, so Lightning automatically finds and uses whatever GPUs or other accelerators you have available. And Precision 16 Mixed uses half-precision floating point numbers, which speeds up training and reduces memory usage quite a bit.
Okay, so we've managed to efficiently fine-tune these giants, thanks to LoRa and the orchestration by PyTorch Lightning. We've got our specialized model saved in a .ckpt file, packed with new knowledge. But you hinted earlier, that file isn't really ready for prime time, is it? Training's done, but the journey to production still has a way to go.
You got it. This is what's often called the last mile problem in MLOps, that trained .ckpt file. It's a training artifact. It contains metadata specific to the training process, maybe optimizer states, and it's inherently tied to the framework you trained it in, like PyTorch. For production, you need something different, something lightweight, fast, optimized for inference, and completely independent of that complex training environment. This last mile involves these crucial steps of optimization and then exporting the model into a standard format.
Right. Let's tackle optimization first. How do we actually make these models smaller and faster for real-world use without, making them dumber?
A really critical technique here is model quantization. Basically, what it does is reduce the numerical precision of the model's weights, and sometimes its activations too. So instead of using standard 32-bit floating point numbers, you might switch to something like 8-bit integers or maybe 16-bit floats.
Integers, like whole numbers. How does that work for complex calculations?
Well, it's a carefully managed approximation. The benefits are huge. You can often get up to a 4x reduction in the model size on disk and in memory bandwidth usage. And inference, the actual prediction speed, can be anywhere from 2x to 4x faster.
So it's like putting the AI model on a serious digital diet. It loses a ton of memory weight and gets much faster, hopefully without losing its smarts. That's a pretty big performance boost.
It is, but there's a catch. If you just take a trained model and naively quantize it afterwards, that's called post-training quantization or PTQ, it can sometimes significantly degrade the model's accuracy, especially for sensitive architectures like transformers.
Ah, okay. So the diet makes it faster, but maybe a bit less accurate?
Potentially, yes, with simple PTQ. That's why for transformers, the better approach is often quantization-aware training, or QAT. With QAT, you actually integrate the quantization process during the fine-tuning loop. You simulate the errors that will be introduced by using lower precision. This allows the model's weights to learn to adapt and compensate for that lower precision while it's still training.
Clever. So it learns how to be quantized accurately.
Exactly. It results in much better accuracy recovery compared to just doing it after training. And in frameworks like PyTorch Lightning, adding QAT can be as simple as adding a specific callback during the training setup. It makes a huge difference in practice for preserving the model's performance.
Okay, makes sense. So our model is trained efficiently with LoRa. It's optimized for speed and size using QAT. Now, how do we make sure it can actually run anywhere, regardless of the server, the operating system, maybe even the programming language being used?
This is where ONNX comes in. ONNX stands for Open Neural Network Exchange. It's become the de facto industry standard for model export and interoperability. Its core value is providing the standardized, common format for machine learning models. When you export your PyTorch model to ONNX, you essentially decouple it from PyTorch.
Decouple, meaning it doesn't need PyTorch installed anymore to run.
Precisely. The beauty of an ONNX model is its portability. It's a self-contained file, usually ending in .onnx, that can be loaded and run by various different high-performance inference engines. The most common one is ONNX Runtime, which is developed by Microsoft. But there are others too, and these runtimes are available for different hardware, CPUs, GPUs, specialized AI chips, and different programming languages, C++, Java, C#, Python, JavaScript. You can run your model practically anywhere, even in environments where installing the original heavy Python training framework wouldn't be feasible.
Wow, okay, so ONNX is like the universal translator, or maybe the PDF, for AI models. You create it once, and then lots of different things can read and execute it.
That's a really good analogy, the PDF for AI models.
Yeah.
Yeah, and a crucial feature for NLP models like our summarizer, when exporting to ONNX, is specifying dynamic axes. This tells the ONNX model that some input dimensions, like the batch size or the sequence length of the text, can vary. This is essential for real-world use because you don't know exactly how long the input text will be for each request. Dynamic axes handle that variability gracefully during inference.
All right, this is great. We've got this optimized, super portable ONNX model file. Now, how do we actually wrap it up so that you, the end user, can interact with it? Like build that text summarization tool on a website or in an app.
Okay, so now we build a web service around it. A common and very effective way to do this is using FastAPI. It's a modern Python web framework that's really well suited for building high-performance APIs. It's great because it supports asynchronous operations, which helps handle many requests efficiently, and it automatically generates interactive API documentation using standards like OpenAPI. This makes it super easy for developers to test and integrate with your service.
And how does the ONNX model fit into that? Do you load it every time someone asks for a summary?
Good question. No, that would be very inefficient. A crucial optimization is to load the ONNX inference session using ONNX runtime and also the tokenizer that the model needs. When the FastAPI application starts up, these become global objects. Then each incoming request to your API endpoint, say summarize, just uses those already loaded objects to process the input text and run inference. This avoids the costly overhead of loading the model and tokenizer repeatedly.
Makes sense. Load once, use many times.
Exactly. And within FastAPI, you typically use Pydantic models to define the expected structure of the request. Like it should contain a field called text,
Yeah.
and the response, like it will return a field called summary. This gives you automatic data validation.
Okay, so we have a web API,
Yeah.
but different servers, different operating systems. How do we make sure this whole thing, the FastAPI app, the ONNX model, the tokenizer, Python itself, all the libraries, runs exactly the same way everywhere, whether it's on my laptop or some big cloud server?
That is the perfect use case for Docker. Docker lets you containerize the entire service. What that means is you package the FastAPI application code, your optimized ONNX model file, the specific Python runtime version you need, the tokenizer files, and all the Python library dependencies, like FastAPI itself, ONNX runtime, the tokenizer library, into a single, isolated executable unit called a Docker image.
So it's like putting your entire application and all its needs into a sealed box.
Precisely. And that box, the container run from the image, contains everything needed to run. This guarantees consistent execution. If it runs in the container on your local machine, it'll run exactly the same way in a container on any cloud server or any other machine that can run Docker. It completely solves the "it works on my machine" problem and drastically simplifies deployment and managing the application in operation.
No more mystery environment issues. That's huge.
It really is. And when writing the Docker file, the recipe for building that image, there are some best practices, like starting from a slim base image to keep the size down, installing your dependencies from requirements.txt early on to leverage Docker's layer caching, which speeds up rebuilds, and using the exec form for the CMD instruction that starts your FastAPI server.
Why the exec form?
The exec form ensures that your Python application becomes the main process, PID1, inside the container and receives operating system signals properly, like signals to shut down gracefully. It's a small detail, but important for robust production services.
Got it. And then, as the sources mentioned, you can actually build this Docker image locally, run the container, and test your summarize endpoint using a simple command line tool like curl to send it some text and see the summary come back. That really brings the whole process full circle, from idea to a working containerized service.
So there you have it. That was a really comprehensive journey, wasn't it? We started right down at the foundations, understanding the transformer architecture, how these models actually understand language with attention mechanisms. Then we navigated the challenge of fine-tuning these huge models efficiently using LoRA, orchestrated by PyTorch Lightning, which Honestly, was a genuinely surprising piece for me, how accessible it makes things.
Yeah, LoRa's impact is massive.
Then we bridged that gap to production, optimizing the model with quantization to make it smaller and faster, and exporting it to the universal ONNX format for portability. And finally, we wrapped it all up, deploying it as a robust, callable microservice using FastAPI for the web layer and Docker for that crucial containerization and consistency. It's quite the pipeline. It really is. And what's truly fascinating, I think, about this whole process is how it highlights a fundamental principle of modern MLOs. It's the power of a modular ecosystem. Notice how we didn't rely on one single monolithic platform that tries to do everything. Instead, we chained together specialized best-in-class tools, PyTorch for the core training, Lightning for orchestration, LoRA for efficiency, ONNX for export, FastAPI for serving, Docker for packaging. Each piece does its job extremely well.
Right. And that modularity, that's not just elegant, it's a massive strategic advantage, isn't it? It means you avoid getting locked into one vendor's entire ecosystem. Engineering teams can independently evolve and optimize different parts of the stack. If a new, even better PE fame method comes along next year, you can potentially swap it into your Lightning module without having to rewrite your Docker file or change your API code.
Exactly. Or if a new inference runtime emerges that's faster than ONNX runtime for your specific model and hardware, you might be able to switch the backend in your FastAPI service without touching the model training code at all. It gives you flexibility, lets you adopt innovations faster, and avoids getting stuck with outdated components just because they're part of a bigger platform. And, with this containerized service now built and tested, the path to deploying it in the cloud is basically wide open. You can push that Docker image to a container registry like Docker Hub or AWS ECR, and then deploy it to managed Kubernetes services, or maybe serverless container platforms, or specialized ML hosting services like AWS SageMaker endpoints. And just as a final thought, for teams already heavily invested in the Lightning ecosystem, there are emerging tools like Lightning AI's LitServe, which aim to make that transition from a trained Lightning model directly to a scalable production API endpoint even more seamless. That represents perhaps the next frontier, further simplifying this complex path from research idea to real-world application that people can actually use, something to keep an eye on.
What an incredible deep dive into the nuts and bolts, the real engineering behind generative AI. We really hope this gave you a valuable shortcut, a clearer picture of how these seemingly magical models actually make it from the lab into your daily life. The next time you see an AI generate something amazing, maybe you'll have a little more appreciation for the complex but really brilliant engineering that makes it all possible. Keep exploring, keep questioning, and please join us next time for another deep dive.